Hey everyone, and welcome to another LeetCode problem. So today we're going to be doing problem number 2699, modify graph edge weights. This problem was in the last LeetCode contest on Saturday, I think, and it was the hardest problem in that contest. So just a quick read. You're given an undirected weighted graph containing nodes from 0 to n minus 1 and an integer array edges where you have a starting edge, an ending edge, and a weight. And some edges have a weight of -1, while everything else has a positive edge. And your task is to modify all edges with a weight of -1 by giving them positive integer values in the range 1 to 2 times 10 to the 9th, so the shortest distance between the nodes, source and destination, becomes equal to an integer target. If there are multiple modifications that make the short distance work, then any of them are considered correct, and return an array considered all edges with your modification, or an empty array if it's impossible. You're not allowed to modify the edges with initial positive weights. So let's take a look at a few of these examples, and let's try to figure out how we can get started with this problem. So first of all, let's try this first example one. So node 2, node 0, node 3, node 4, node 1. And from 4 to 1, there's an edge of -1. From 2 to 0, there's an edge of -1. From 0 to 3, there's an edge of -1. From 4 to 3, there's an edge of -1. Okay. So we're trying to get from node 3 to node 1. And as you can see, so there's only one path here. So this path is going to be like this. And obviously, we can also tell that there is a way to modify these. So one thing you can see straight away is the smallest value you can modify all of these edges to are 1, because they can't be negative. And because you can modify any one of these values to up to 2 times 10 to the 9th, we can just take every edge, every negative edge, and make it equal to 1. So like let's say we make all these equal to 1. And then we can just figure out how much more do we need. So if this is 1, 2, 3, we need 5. We can just take any edge and increase it by whatever we need left. And because the maximum the target can be is also, I think, 10 times 2 to the 9th. Oh, let's take a look here. Target, yeah, 10 times 10, or it's just 10 to the 9th. So we can always increase one of these edges sufficiently to make our path equal to the target. So we don't have to modify more than one edge. We should be able to just modify more than one negative edge to make it big enough so our path is equal to the target, and leave the rest of them equal to 1 in our shortest path. Now let's take a look at another example. Okay, so we're given this one. Oops. 0, 1, 2. Okay. And 0 to 1 is -1. 0 to 2 is 5. Our target is 6. So we're trying to get from here to here. Now you can see the only path here is this, and we cannot modify a positive edge, which is already 5, so we can never get a target of 6 going from 0 to 2. So that one is pretty straightforward. Let's go to the next one. So we have 2, 2, 3, 0, 1. These are all connected. Okay. Now our edges are 1 to 0 equals 4. By the way, since this is an undirected graph, 1 to 0 and 0 to 1 would be the same edge. So that's also going to be important for when we actually fill out some kind of something to store these edges. So this is 3, 2, 3 is 5, 0, 3 is -1. So we're trying to get from 0 to 2. Okay, well, what paths can we take? So we can take this path, which would be 7, or we could take this path. Our target is 6, so we can see that we can just change this edge to 1, and then that would give us a valid answer. We would be able to go here. So another example that they don't show you that's also going to be quite important is, so let me demonstrate that. So let's say we're trying to go from node 2 to 1, let's say maybe to 3. So we're trying to go from 2 to 3. And let's say our edge lengths here are this, And now let's say we'll just make it easy, I think. We'll just do something like this 6. And our target equals 8. Well, what would happen in this case? So there's a couple things we can do. First of all, if we do a shortest path algorithm, by the way, we're going to be using Dijkstra's shortest path algorithm. Dijkstra's, I don't know how to pronounce it too well. Let's just call it Dijkstra's shortest path algorithm. So from here, if our nodes are -1, then our shortest path is going to be this. And then we want 8. Well, can we do that? Yes. We can make, once again, so if our nodes are -1 or 1, either way, it's going to be the shortest path. So let's just say we take every negative value and we make it 1, because that's the smallest possible value, is to start off. So let's say we do that. So these are 1 and 1. Now our shortest path is going to be 2, and we need to increase it by 6. So how do we do that? Well, we just take one of these nodes and we make that 7. But the problem is, now that we increased this node to 7, our shortest path is no longer this, because this path is 8, but this path is 6. And so we can't make this path equal 8 and still have it be the shortest path. So here we should actually be returning a no solution. So this is one of the edge cases that it took me a long time to figure out for sure. Because I would get a shortest path with these negative nodes, and then I would be like, okay, well, all I have to do is change one of these negative nodes to 1, and then, or to whatever value I want, and then I'm good. But that's not the case. Another really easy example with something that was going to be tricky is, let's say we have this. So we have 2 to 3, then let's just say, I don't know, 4 to 3 or something. So let's say this is -1, this is -1, this is -1, and our target is 8 or something. Target is 8, again. So our shortest path, and let's just say, like I said, we make all these values 1 to start off. Our shortest path, if we're trying to go from 2 to 3, let's say, our shortest path is going to be 1 here, and we need to make it increased to make it 8. Well, we can do that, so we can make this an 8. But once again, if we make this an 8, this path is now the shortest path. So the way we're going to fix our issue, if we have multiple shortest path, like let's say, or not even multiple shortest path, we have a shortest path, but then there are some other paths that might be shorter after we change this. So if these values start off greater than 1, then obviously there's a no solution here because we can't change these values. But if we can, what we can do is we can just take every path, every -1 value that's not on our main path, so let's call this our main path, 2 to 3. We can take every value that's not in our main path and we can just make it the max. So in here the max is 2 times 10 to the 9th, and then the target is going to be 10 to the 9th. So if we just make every other negative value, so these 2 times 10 to the 9th, and this 2 times 10 to the 9th. Now our shortest path is still this, and we have a solution. So these are the two important cases: is if we change these, do we still have a shortest path? And so the way we're going to handle this one on the left is we're going to be using Dijkstra's algorithm. Now we're going to have 3 values. We're going to have a number of negative integers. So let's just say in each thing in our heap for Dijkstra's algorithm. Let's say we're going to have here, let's just say negs or something. So this is the number of negative integers in our path. This is the path length. Let's just call that L. And this is the actual path. So let's just call that P. And so what we're going to do, because our heap is going to take this value and care about it the most, we're going to take every single value that has no negative values and go through those first. So this path would actually, even though it's smaller, we're going to care about the number of negative values first instead of the length of the path. So therefore, we're going to take a look at this path. We're going to say, okay, this path is 6. It's below 8. Therefore, we have no solution because we have a path with no negative values. So whenever we modify some other path to be 8, this path will be the shortest. And now in this case, because here we have negative value 1 and here we have 2, this path will actually get processed and we will say we do have a valid solution. Okay, so just to clear that up again, we're going to use Jix's algorithm. We're going to find the shortest path. We're going to make sure that shortest path actually has negative values. If not, we have no solution. And then once we do find the shortest path, we are going to figure out, let's just take any negative number on our path, increase it the right amount to make it equal to target. Let's take every other negative value that's not in our path and make it the max. Therefore, any other path won't be shorter than our shortest path. And that's going to be guaranteed because, once again, if we have multiple paths, if we make all these paths huge and we only increase this one by a little bit, the most we can increase this value is to 2 times 10 to the negative ninth. So if this is the shortest path to begin with, and there's some other path with another -1 value, if we increase two values by the same, but this is the shortest one to begin with, it's guaranteed to be the shortest path. Okay, so for this one, we're going to take a look at the code, and I actually coded this up beforehand because I ran into a lot of errors and there's just a lot of code, so I don't want to have to debug code. I'm just going to go through what everything does. Okay, so first of all, we're going to have a paths dictionary, and it's going to be a dictionary of dictionaries. And so this paths dictionary is going to, the first key is going to be, so like for example, if we have something like this, I'm just going to comment this on the top, paths of x, y, meaning it's the path from x to y, and it's going to have some weight. So these paths, there's going to be a dictionary for every single n node, and then the keys are going to be the nodes that it's connected to, and then the values are going to be the weight. So for example, like here, this 0 will be a dictionary. Yeah, it'll be a dictionary with this value, and then this 1 will be a dictionary. So this will actually be a key in the first dictionary, this will be a key in the second dictionary, and this will be the value. So this is kind of what it'll look like. We can return things like this. Paths x, paths y. So x will be the key here, y will be the key in the second dictionary. Okay, now we also have a set for negative edges. And this set is going to be a dictionary with a set in here, meaning if we have something like this, edges x, it will mean what are all the negative edges that start for this set. So like let's say this is 0, for example. This will be what are all the negative edges that start at node 0 and go to some other node. So it can be from node 1, node 2, whatever. We don't need a weight because we know they're going to be -1. So instead of having a default dict of dicts, we can just have a default dict of sets. Okay. Now we're going to iterate through these edges. We're going to take a left node, a right node, and a weight. And then, like I said, when there's a negative weight, we are going to add this as a negative edge. And because I also said that this graph is undirected, if there's an edge from 2 to 3, there's going to be an edge from 3 to 2. So I just added both of these. So neg edges left, add right. Neg edges right, add left. Okay, and then we're going to change this weight to 1. And then we're going to add that to the path. So for every number that's -1, we're going to change it to a 1. Then we're going to heap for Jix's algorithm. So Jix's algorithm normally uses a heap because the way it works is we take the smallest vertex, the smallest edge that's available that we can travel to a non-visited node. And that you can look that up. There's actually a LeetCode video on it as well. So then we're going to have this best path, and this best path is going to be, when we do find a best path, we're going to check, is this a valid path? And then we have a best path length. So we have a while heap. This is basically going to go through our heap until we get to a valid point. Then we have negs, which is the number of negative numbers. We have weight, which is the distance. And then we have the current path. So we pop from the heap. So for example, here, we're going to pop distance 0, weight 0, and then our source node. Then we're going to say, if our last node in our path, so this path is going to look like something like this. when we're going to keep appending to it. So it'll be like 0, then let's say we append some ancestor of 0, 1, 2, whatever. We're going to keep checking this last thing in the path, and we're going to say, is this equal to the destination? Because if it is equal to the destination, that means we've arrived to the node we want to be at. So if it is equal to the destination, if negative numbers is greater than 0, that means the first path that's greater than the destination has a negative numbers greater than 0, and our weight has to be below the target because we're only putting items into the heap that have a weight smaller than or equal to the target. So this weight has to equal the target or be below, which means we can always add something to our negative number to make our shortest path viable. And for those other examples, like let's say we get here and all our numbers, like if our target's 8 and we get to this node, but all our numbers are positive, and it has a smaller weight than the target, then that's no good because that path would be invalid. So if our target's 8 and then we have a path 6 and every number is positive, we can't possibly make that number any bigger, so that would be an invalid input, and then we would just return this. Okay. So as soon as we find something, we're going to break here, and I'm going to talk about that at the end. But so let's say we didn't get to our destination. Now what we need to do is we need to take the node that's at the end of the path, and then we need to take every single node that's connected to that node. If that node is already in our path, we can continue because it's already in our path, so we don't need to do anything. And then this just calculates the new negative numbers, the new weight, and the new path by adding. And so now we check, is our new weight, is our total path length less than or equal to the target? If it is, add it to the heap. If not, we don't care. And so we don't need a visited array. Normally when you do Dijkstras, you usually have a visited array to make sure, did I already visit this? If I didn't, then I can visit it. But here we don't need to have a visited array because we're just going to keep adding. And so like for this example, let's say we start here, we just keep adding, and then eventually, since we keep adding, eventually our number is just always going to be greater than the target, and that's kind of like our stop condition. We just keep adding until we're greater than the target. Okay, so this is going to check if we have a valid best path. So remember, the only way to have a path of non-negative numbers is if it equals the target exactly. So for example, let's say we're trying to go from 3 to 1, and our target is 8, and let's say this is actually 5 and 3. Then this would be 8, and this would be a valid path, and it would be the shortest path, and it would be fine that these numbers are immutable. But if this whole sum is less than our target, then we can never achieve the shortest sum equals target because we can't change these numbers. Okay, so that's that. So now we figure out how much we need to add. If we have a valid answer, how much we need to add. And so if this let me look here. Okay, so if weight is equal to the target, this what we have to add would be 0, in which case we would just take every node on the path and not have to add anything. So let me show you how this works. So we make a set of negative numbers, and then we iterate through every single number on our path, and we add the combination of, so let me just show what this looks like real quick. Let's say our path is like this. We are going to iterate from every single number up to the second to last number, and then we're going to add that and the number right behind it and the reverse. So for example, if we're at 1, we're going to add 1, 2. And we're going to add 2, 1 because either edge is the same, because these edges in our edges are not guaranteed to be in the same order as our path. So we need to add both. So that then we go to 2, we would add 2, 3, and then 3, 2. So these edges in our path would have to go from 1 to 2 and 2 to 3, but they can be in any order. So we would have this set of every single set of negative edges that's in our path. Actually, it's not, sorry. So this should actually be, this is technically not a negative edges set. This is just a set of all the edges in our path, I believe, actually. Yeah. Yeah, so this shouldn't be called path negs. It can just be called like edges on path or whatever. So we add them. Then we have this output array, and this is going to be what we're going to be outputting. This is going to be the edges that are outputted with the modifications. Then we just loop through this edges array. If the weight is greater than 1, that means we can't modify it anyway. And by the way, we didn't modify these negative ones in the edges array, so they remain as this. So if we go through this first one, they will look like this. We didn't modify them in here, we just modified them in the dictionary. And so if the weight is greater than or equal to 1, we can just append straight away because we can't change it. Now, the other conditions are if it's negative. So if it's negative and it's in our path, so this, like I said, this path neg should actually be just path, like best path nodes or something. What we can do is we can append the left and the right. We can add for our first one. This is how we're going to handle adding to our first negative edge that we encounter. This was the difference between the target and the best path. So let's say our best path is 6 and our target's 8. That means we know we need to add 2 to one of the negative nodes. And so we would handle it here. We would add to here. Then we would, as soon as we added once, we're going to make this 0. So then in the future, we're just going to add 0. And remember that if the edge is negative and it's not on our path, we're going to make it the max value. So that way it's guaranteed that the other paths are longer than our target path. Okay, and then we're just returning. So let's think about the time and space complexity here. It's going to be pretty tricky, and I might get this wrong, but let's think about it. So it's not O-van, I'm just writing here, by the way. So what are we doing? We are making these two path things. So it's going to be a dictionary of weights. And the most this can be, I believe, is edges. Like the most number of combinations should just be edges, I'm pretty sure, and vertices. So it should just be some kind of E plus V because we can have a vertex 1, vertex 2, and then we have some edge. We have some edge weight to it. So it should just be E plus V, I think. It might be like 2E plus V, but that we can get rid of that for a big notation. So then we have this set that has neg edges. Now these neg edges, this is going to be smaller than paths, so that's going to go to 0. And then we have a heap where we do keep adding paths. And so that's going to be kind of tricky. I think that would be because it's kind of hard to say how many paths we can have on the heap at one time. Sorry, my mic cut out for a second. So it's going to be hard to say how many paths we can have on the heap at one time and how many nodes. But I think the longest path possible would probably be something like you have all the number of edges total, and then the longest path would just be path. So like you can have 1, 2, 3, 4, 5 edges total on the heap. I think if you made their distances in a way where you wouldn't really be popping, you would just keep like adding, or I'm not entirely sure there, but yeah, you would make it in some order that would maximize heap size. So I think that would be something like you can have up to V nodes where V is a vertex, and then each node can have distance something like V as well, so it might be like V squared. Not entirely sure there, but I think something like that. So let's just, yeah. And then there's a heap. And now this stuff is should all be smaller. This should just be edges, and then so our dictionary is something like this. And then our heap, I think the most it can have is V, or would it? No, let me think. If it would be V, or actually it would be number of edges. I think it would be number of edges times, I think something like this, because we can have, so then this would just go to this. But once again, I'm not entirely sure for this heap thing, because if we have a lot of items on the heap and each one has a long path, then that's going to get tricky for sure. Okay. Especially if we have some weird tree that's like just goes off in a bunch of directions, like this goes off here, this goes off here, and so on, where like it's all equally, it looks kind of like a tree, but every single one of these nodes would and let's say these distances are in a way where it goes here, then here, then here, then here, then here, then here, and then this is the destination at the end, we would have n over 3 nodes, which would be 3, and then each node would have n over 3 path, which would be also, sorry, n over 3 nodes, which could go to n, and then n over 3 path, which I think would be n. So it would be, I think it would be something like e times v or v times v or something along the sort. Okay. So space complexity is going to be, so for this dictionary, once again, we're going to have this e plus v thing, e times v. So actually, I think I flipped those over. So I think the space complexity should be this, because I think this would be the maximum size of the heap. So actually, let's go look at the time complexity and figure that out. Okay, so we go through all the edges here, so that would just be length of edges, pretty simple. Now, how many times, like I said, how many times would we iterate through the heap? Well, we can get to the same node actually multiple times with our algorithm, because I showed in the previous example where we can loop, definitely, because we can visit the same node multiple times as long as it's less than the target. So once again, this heap space complexity is going to be a little bit tricky. What you can maybe do to improve this, and I would encourage you to try this on your own, is maybe to have some kind of visited set, and try to run it with that where you're not revisiting the same nodes. Okay, and then that's nothing, and that's that. So I would say this is, it's really hard to say. It would be like the most items you can have is maybe you're adding. So let's say you're adding, and it's like target. If you're just adding 1, 1, 1, 1, 1, 1, 1, and so this can have something like, if every node is connected to every other node as well, it would be kind of tricky. So this target would actually round to 0, but actually no, it wouldn't round to 0, because this can be a really big number. So honestly, yeah, I think if you were given an interview question, you could just say something like, well, it's going to depend on my target, because our target can be really big, so this can be really big. Okay, and so yeah, it could be something like target times, let's say v, where like v is the number of vertices, but once again, I'm not entirely sure on these. Okay, so I would say for this problem, I would encourage you to redo it. There are a lot of algorithms you're using. You're using a heap, you're using dictionaries, you're using traversal, and honestly, for this algorithm, it's one of those that, like, even if you know exactly what to do, it's very easy to miss edge cases, and it's still not easy to code. Like, when I figured out that for negative numbers, you can find the shortest path by making all these negative numbers 1, because that's the smallest number you can make. There's still all these edge cases, like I showed you, with all these, different, like, if a number is smaller than the target. It's something that I would encourage you to code multiple times, and it's also why I didn't want to code this on the fly, because I thought I'd make a decent amount of mistakes. Okay, so that's all for this problem, and I'll see you in the next one.